some of the basic motivations behind these things. I consider the main motivation to be, mostly there's classification, but there's also the fact that when you start with an algebraic variety, set of zeros or polynomials in projective space, and usually these things are complicated, they're not linear, and they have a lot of structure. So if you want to study them, if you want to classify them, it would be good to find some invariants that are simpler than the variety itself. And so a good thing would be if you could find invariants that are linear in some sense, because the varieties themselves are very far from being linear. So one thing that is sort of linear is a Hodge structure. Now I'm not going to get into that yet, but let me start with some very classical constructions, which is where the whole story basically started in the 18th and in the 19th and 20th century. So let's or abelian varieties. And as I said, these objects are linear in some sense, that we're going to see how. So let's start with a classical construction of a Jacobian, of a Riemann surface. So let's say that C is a smooth algebraic curve over the complex numbers. So it will look normally like a Riemann surface. I mean, it is a Riemann surface, right? And those of you who are familiar with them know that logically they can be sort of drawn like that, like a torus with many holes. So, no, actually, I don't need color for that, sorry. Okay, so, and as I said, even these things can be somewhat complicated. So, and they are nonlinear. So we want to associate a linear object to them, which will be an abelian variety. And we call that the Jacobian of the curve. Now maybe in the old days this is not how it got started. It started mostly with people trying to integrate differential forms on the surface. So classically this is what people wanted to do. They wanted to integrate differential forms on C. Okay, now what's a differential form? I'm going to talk about holomorphic non-forms. And that means that locally, what does it look like? Locally, it looks like some holomorphic function times dz, where z is a local coordinate or in a neighborhood of a point. So if you have a little chart, if you have a little point on there, and you have a small chart, so let's say that's one point P, and you're going to have a neighborhood of the point, and I have a little coordinate center at P, right? And, well, locally I can draw a path here, and I Now people said, okay, this is all very nice, but we really want to study the Riemann surface, and we kind of want to, we would like to have an integral that doesn't depend on the path. So say we want an integral which depends only on the points, not on the path. Oh, maybe I should have changed the board. Okay. Okay, so the question is, can you compute the integral from P0 to P of your differential form omega? And the problem is that, okay, so you can choose a path from P0 to P and integrate your differential form on that path, but it's going to depend on the path. And people don't like that sort of thing. They like things to not depend on some random things that they cannot determine, right? So sometimes you can choose, I mean, first of all, of course, they started thinking, well, can we choose a nice path, which is unique in some sense? And the answer is kind of no. You see, I mean, if you had just a Riemann sphere, and you take 2 points on it and you go from one point to another with one path, then if you choose a second path from one point to the other, it turns out that the 2 paths are what we call homotopic. That means you can move one path into the other. And because of this, the integral on the first path is equal to the integral on the second path, right? So if you didn't have any holes in between the 2 paths, you'd be okay. So if gamma 1 is homotopic to gamma 2, again, that means that you can continuously move one path into the other, right? Then the integral over gamma 1 over omega is equal to over gamma 2 of omega. But that surface up there has got holes in it. So even in the very simple case, in the simplest case of one hole, I could have my point P0 here, I could have P here, and that could be my gamma 1, and then gamma 2 could be there. Now you see, it's not true anymore that the integral from one path is equal to the integral from the other path. In fact, if you take the difference, right, these are oriented paths. Sorry, I should have said that. So the integral over gamma 1 of omega is no longer equal to the integral over gamma 2 of omega, right? Or you can write that differently. You can write this in a different way. You can say that the integral over gamma, yes? Somebody said it. Gamma 1 minus gamma 2 of omega is not 0, right? So this is the problem. This difference between gamma 1 and gamma 2, it's what's messing up our business, right? And that difference, what is it? It's a loop. We fixed this point P0. That difference is a loop starting at P0 and ending at P0, right? Based at P0. And so that was basically, that's the answer. That's what you want to do. You want to get rid of these integrals of the differential form on loops centered at your fixed point. Okay? Alright, so let me introduce some notation now. Let me say, let me call H0 of little omega c, or actually let me call it big omega 1 c. This is the space of holomorphic differential one-fourths on C. Okay? And then I need to talk about the loops, where I can talk about the loops on C, H1 of C. This will be the space of loops on C with some base point, if you like, with a base point. But the base point doesn't really matter, right? Because I have a loop again to a homotopic loop, the integral will not change if I wiggle a little bit, if I wiggle my loop around a little bit. So, but that's what we're interested in. So what we have here, we have basically an action of this on that. So okay, so whenever you take an element of H lower 1 of CZ, this acts as a linear form on H0 of omega 1 via integration. So omega goes to the integral of omega on gamma. Okay? And as we said, the ambiguity, if you want to integrate from one point to another, the ambiguity is exactly these things, right? If you choose different paths, the difference between two paths will be a loop. So what people did was they said, so the interesting object here for us is going to be, we're going to take the space of linear forms, and we're going to mod out by the guys that come from the loops. So H lower 1 of CZ, and we're going to call this the Jacobian. Now we have a well-defined map actually from the curve in here. So the integration now works. Okay, so if you choose a fixed point P0, then you choose an arbitrary point P, right? Then you have a map from C in here into JC, which sends P to the integral from P0 to P of omega. And now I have no ambiguity anymore because I killed the ambiguity. Right? So I can integrate from P0 to P, I can just choose a path, and it doesn't matter what path I choose because the difference between any two paths will be an element of this guy, and I killed this guy. Okay? Alright. Now this is a nice object, so that's the abelian variety that I was talking about, right? This is the Jacobian variety. Named after Jacobi. And this guy is called the Abel map. It's one Abel map. And you have the Abel-Jacobi theorem, which says that this map is actually an embedding of the curve into the abelian variety. What this guy looks like, what does this guy look like? Let's look at it a little bit more closely. So you have this H0 of omega 1, H0 of omega 1, and we take its dual, right? This guy, you can show that it's isomorphic to the complex plane, and the complex plane to the power of G, where G is the genus. It's the number of holes in the Riemann surface, right? And then you can also show that H lower 1 is isomorphic to Z to the 2G. Okay? So what you're doing here, you have a complex space of dimension G, real dimension 2G, and you're modding out by what we call a lattice. So this is an abelian subgroup here of maximum rank. And so the quotient, when we take that quotient there, it's going to be what we call a complex torus. In this case, it's an abelian variety because it's actually an algebraic variety. You can prove that. So basically, this JC topologically a product of S1s. So S1 times S1 times S1 2G times. And it has, it has a complex structure, because that's why we call it a complex torus. It actually has an algebraic structure, and that's why we call it an abelian right. Okay. Any questions so far? No. All right. And let me just say one last little thing about why you have 2G independent loops. And let me also draw the donut here. So the independent loops, the independent non-trivial loops, are the ones that you cannot contract, right? If I don't want to be able to contract the loop, I have to go around the hole, right? So that's one. That one is not contractible. And then I've got another one. I can go around the hole this way, right? That's another way of going around the hole. So you have these two. You see, this is genus 1. So I have two independent loops. That's why you get a Z2 here for genus 1. And if you have genus G, you're going to do the same thing. You can go around each hole. And then you can go around the other way. Yeah. So you see you have 2G. All right. So you started with a curve, which is a nonlinear object. You associate it with a Jacobian, which is a linear object. Now you can ask whether you can get the curve back from the Jacobian. What if somebody gave you the Jacobian and they asked you, well, can you recover the curve from it? And the answer is yes, and that's the classical Torelli problem, Torelli theorem. Okay? So, question. Given JC, can one recover C? Okay? And the answer is yes. Now there was the first answer to this. The first proof was by Torelli himself in 1950. And then there were many other proofs. Other people came along, like Andreotti, Matsusaka, Martins, and possibly even others. I'm not sure. And they gave many. There are many different proofs of this in the literature. Okay, and each of those proofs is interesting in its own way, because each of them exploits some other geometric aspect of the Jacobian. Some of them are longer, some of them are shorter. Anyway, so it's you don't need. The thing is, the Jacobian. One thing I should mention: the Jacobian comes with some extra information, which is its polarization, and you actually need the polarization. I don't want to get into that too much, but anyway. Okay. And as I said, from the point of view of classification, this is very nice. Why is that? Because, so let's say you want to classify the curves, right? So what you do, you can put all the curves into one big algebraic variety, which is called the moduli space of curves. Of genus G, you fix the genus, and then you let the algebraic structure vary, right? and you get this, you get some algebraic variety. The dimension is 3g minus 3. If g is at least 2. It's dimension 1 if g is 1. And 0 if g is 0. Basically, there is only one Riemann sphere. There's no more than one. Okay, so and then you can make this moduli space whose points give you curves. So basically, a point of the moduli space is a curve of genus G. And you can do the same thing for these abelian varieties, right? So you can make the moduli space AG. And they have to be, as I said, there's a polarization, and we're going to put the polarization together with the abelian variety. That's some extra information that comes with it. And we will take them to principally polarized. Moduli space of principally polarized abelian variety. And then you have what we call the Torelli map. AG, and it's what we talked about, what we just talked about. So you take this curve C here, right? It's a point there, and you're going to send it to the Jacobian. So that gives you the abelian variety. And there's another way of saying the Torelli theorem. It says that this map is injective, right? That's nice. So when people see something, a nice picture like this, they always try to see if they can do this for other things, right? So there were people tried to do this for higher dimensional algebraic varieties, and people tried to do this for other constructions with curves, right? Constructing the Jacobian was one construction, but you can do other constructions with curves, and you can again get maps into moduli spaces of abelian varieties, and you can ask the same similar questions about that. Okay, I don't know how much I'm going to be able to do exactly, let me first start with the things with curves. So you look at that map. I mean, you have two. Actually, both of those varieties are kind of nice. They're almost smooth. Not quite. You have some finite, what we call finite quotient singularities in some places. So the mg I said was dimension 3g minus 3, but the ag, you can compute the dimension of ag. And it turns out that it's g times g plus 1 over 2. So you can see immediately that even though the map is injective, it cannot possibly be surjective as soon as G is larger, right? So the Torelli map, T, I didn't call it T, so T from MG to AG is not surjective as soon as G is greater or equal to, I think, 4. Okay, so then people start saying, well, okay, so we have up to genus 3, we have all these abelian varieties, they all come from curves. You can get them all from a construction from curves, but as soon as G is at least 4, you have some extra things that cannot be Jacobians, right? So, and then, if you've been playing a little bit with Hodge structures, these these, you know, this H0 of omega 1, etc., is a piece of what you call a Hutch structure of weight 1. And philosophically, people like to get Hutch structures of weight 1 from one-dimensional things. They don't like to get them from two-dimensional things. So you have all these Hutch structures of weight 1 in AG, and you cannot directly get them with the Jacobian construction from curves, from one-dimensional things. So then you can ask, can you get them from curves somehow by other constructions, right? The Jacobian is one construction. And the first construction that people came up with was the construction of a prim variety. So there's other constructions. With curves producing abelian varieties. And as I said, the first example of that, and these constructions will give you bigger chunks of the moduli space, and eventually, actually, you can construct what people call a prim-Turin variety, and you will get everything, okay? But let me start first with prim variety. So you get bigger chunks. I'm just using this book. I got confused, sorry.
There's a border.
Maybe no, get used to switching them. I keep using the same one. Okay, so let me explain what's a prim variety and how do you make it. When we make the Jacobian, we just took one curve, right? Here, what do? You take the curve with some extra data. And it's the same thing for prim-Turin, the thing that I just mentioned. So you start with a curve with some extra data. And in this case, the extra data is a double cover of the curve. So C tilde to C, an unramified double cover. Let's see whether we can possibly actually catch more of AG, right? So what kind of first let's count the parameters for this, and then we will construct the prim variety and see how big that is. If you start with a curve, well, okay, that's 3g minus 3 parameters, right? The dimension of mg was 3g minus 3, and if you add the data of a double cover, you're only adding a finite amount of data, because for every curve, the number of double covers is 2 to the 2g minus 1, and non-trivial, right? I don't want this to be trivial. Okay, so there's a give. If you fix the C, there exists a finite number of unramified double covers at C. So this will give you a moduli space, just as the case of curves, of such double covers. And usually people call this RG, right? And it turns out because the extra information is finite, this has the same dimension as mg. Again, that's for g at least 2, 1 if g is 1, and 0 if g is 0. No, wait a minute, if g is 0, actually it doesn't make sense. Then I said it was non-trivial, so. Okay. Alright. And now we're going to construct a prim variety. Alright, so you can construct the Jacobians of both curves. And it turns out that there's a map from one Jacobian to the other. And we call that map the norm map. here what do we have? We have the space of differential forms on C tilde, and then we have the space of differential forms on C, right? So you can pull back differential forms, basically in the same way that you can pull back functions from one curve to the other. You can pull them back, so the map goes in the other way. And then if I'm looking at the duals, then I will go from C tilde to C, right? And then with the loops, it's even easier. You just take a loop here, you take its image down there. Okay, so the loops, you can just push them forward. Which one of C tilde T, not C, which one of CZ, and that's what produces this norm map from one Jacobian to the other. You take the quotient of this by this maps to the quotient of that guy by that guy. Okay? And so this one is a nice abelian variety. The dimension of this guy is G. If you can compute the number of holes here, the genus topologically. You can see how it lives. And this one has got genus 2G minus 1. You'll get 2G minus 1 holes on the double cover. And it turns out that you can also prove that this map is actually surjective. Okay? So it's going to have a kernel. The kernel of the norm will have dimension. First of all, the dimension is the difference between the two dimensions. The dimension is going to be G minus 1. Right? And then you can compute what it is. It's going to be a unit of two things. It's going to be a unit of one abelian variety plus a translate of that abelian variety. So by a point of order 2. So you have one abelian variety here in the kernel, and the other abelian variety. This guy is the component of the identity. This is a subgroup. Sorry, I forgot to say about the group structure. There's a group structure on the Jacobian, which comes from addition on the vector space. This is a vector space. You can add things in the vector space, and it induces addition on the quotient. So you get an abelian group structure on the Jacobian, right? And I'm looking here at the kernel. This is a homomorphism of groups, and I'm looking at the kernel of this homomorphism of groups. Here it will correspond to the kernel of the map of vector spaces. And this P is the component of the identity in the kernel. And this is what we call the prim variety. So the prim variety of the cover, C tilde to C, that's P of C tilde to C, and by definition, it's this component of the identity in the kernel. But there are other things that I can get from Jacobians. So here you have a big Jacobian, you have a small Jacobian, then you can take the difference. The prim variety is basically the difference between the big Jacobian and the small Jacobian. And it's not unreasonable to hope that you can get more abelian varieties that way, right? Than you did with just the Jacobian construction. And because the dimension here is G minus 1, you do get a bigger piece of the moduli space. So you get a map, you get a prim map, P from RG to AG minus 1, right? And now here, this guy has got dimension AG minus 3, and this one has dimension GG minus 1 over 2. So, and, okay. And people have proved that this map is, basically the dimension of the image is equal to 3G minus 3. So the dimension of the image is 3G minus 3 if G is at least So then the other cases are if G is 5, if G is 5, you're going from R5 to A4, and it turns out that the map is actually surjective. So the prim map is surjective. For G less than or equal to 6, actually. So that's better than what we had before, right? It couldn't be surjective for G greater than or equal to 4 for the Jacobians, but here it is surjective for G at most 6. Okay. All right, but okay, so that's the surjectivity. What about the injectivity? You have the Torelli map is injective, right? I erased it, sorry. Okay. Yeah. The Torelli map was injective in all genera. So you could ask the same question, what about injectivity of the prim map? The answer is no if G is at most 5, just for dimensions reasons, right? If G is, for instance, equal to 5, you have R5 to A4. This we said is dimension 4 times 4 plus 1 over 2, dimension 10. This is 3 times 5 minus 3, that's 12. This guy's bigger than that guy. So it can't possibly map injectively to it, right? And the same thing for G equals 4. You have R4 to A3. And again, now this guy here is dimension 9. And this has dimension 6. So it can't be injective again. But as soon as G is at least 6, there is hope for injectivity. So is P injective? Okay? And again, the answer is no. So there were counterexamples given by. I'm not sure exactly who gave exactly the first counterexample. I thought it was. I think it's Bovio who gave the counterexamples for genus at up to 10. Okay. But then people said, well, okay, it's not injective, but there's another notion in algebraic geometry which is generic injectivity. So P is generically injective for G greater than or equal to 7. And that is due to many people, Friedman Smith, and Velters, I think. They gave independent proofs which were different. does generic injectivity mean? It means that, so what does this mean? It means that you can find, basically, if your curve isn't too special, then the prim map is injective. That's what it means. So you have this moduli space AG minus 1. It means that you can find an open subset of AG minus 1. Sorry, no. It means you can find an open subset of RG such that when you restrict the map to that open subset, then it's actually injective. Okay? That's not quite correct. I'm sorry, but I think if people know what it means, then they know what it means. If they don't know what it means, if I say anymore, it's just going to confuse you. So, if you don't know what it means, just think of it that if you just throw away some special curves from RG, then the map becomes injective, right? That's what these guys prove. If G is equal to 6, that's the missing case. It's not generically injective, but it is what we call generically finite. So again, if you throw away some special curves, then the map has got finite fibers, meaning you can only find a finite number of double covers going to the same point. Okay? And Donaghy and Smith computed the degree to be 27. And it is very much related to the 27 lines on the cubic surface, for those of you who know about that. It's a very nice construction. Okay, so all right. So now there's the question. It's like if you have a question, yes is a very nice answer. You know exactly what it means. But no is a very complicated answer. Because you're saying, okay, this is a yes to generic injectivity, but it's a no for injectivity. And if you're saying, well, the map is not injective, then you're going to ask yourself, where exactly does it fail to be injective, right? So what are those special double covers where the map is not injective? And this is important also for other reasons. Prim varieties are also, for people who know about them, often intermediate Jacobians of higher dimensional varieties. So to know when you get the same thing, that's important because it also tells you something about that higher dimensional variety. Anyway, so, okay, so here's another question. When does the map, and of course we want to assume genus at least 7, right, because we know it's not injective up to genus 6. When does the map fail to be injective? Okay, as I said, there were some examples of Bouville in no genus. Mumford did a computation for hyperelliptic curves, which shows that it's never injective if the curve is hyperelliptic. So never injective. A hyperelliptic curve is a curve with a map of degree 2 to P1. These are very special curves, and if you compute the prim variety of a hyperelliptic curve, it turns out that it's actually the Jacobian of another hyperelliptic curve. So again, for dimension reasons, basically, because you're going from a hyperelliptic locus of higher genus to a hyperelliptic locus of lower genus, for dimension reasons, it cannot be injective. Okay, so, but that situation is completely understood because Mumford described it. So we're going to assume now that the curve is not hyperelliptic. Another question, okay, well, could it be injective at non-hyperelliptic curves? And there's there's a very nice construction of Donaghy, which shows that if the curve, now the hyperelliptic curves had maps of degree 2 to P1, right? And this one is for curves that have maps of degree 4 to P1. So whenever you have, so if C is tetragonal, then the prim map is not injective at any double cover of C. That's the theta divisor. And it turns out that in genus at least 7, that divisor on the prim variety has got singularities. And and the singularities are classified into two different types. There's the stable ones and the special ones. The special ones don't exist on a generic prim variety. They only exist on some special prim varieties. The stable ones always exist. Now it turns out that if the curve is tetragonal, then that special locus of singularities is big. It's uncharacteristically big. But if the curve is not tetragonal, it's actually too small. It's smaller. So that kind of makes grounds for making a conjecture that maybe the tetragonal curves describe the entire locus where the map is not injective. So that was a conjecture of Donaghy. He said that this is it, right? This is the only locus where T fails to be injected. This conjecture in 1981, and together with the construction, and it took a while for anybody to come up with a counterexample. That was in 2004. Vera came up with another example of double covers which had the same prim variety. So he produced some plain sextants. So there exists C, which is a plain sextant, meaning the zero set of a polynomial of degree 6, such and double covers C tilde to C and C prime tilde to C, which are non-isomorphic. Sorry, no, just a minute. There exists, how did they see this example? No, the plain sextants were different. There exists plain C and C prime, plain sextants, with C tilde to C non-isomorphic to C prime tilde. C prime, actually the curves themselves were not isomorphic, the C and C prime, and the same prim variety. He did this actually by using higher dimensional varieties. He used conic bundles. He had a conic bundle with two different. He had a threefold with two different conic bundle structures. Basically, two different maps to P2. He had this threefold with two different maps to P2, and that allowed him to write the intermediate Jacobian of the threefold in two different ways, as two prims, like this. Okay. And then he also showed that these were not tetragonal. these curves did not have maps of degree 4 to P1. Okay, so that complicates the situation a little bit. So now you're wondering, okay, so where is the locus? Maybe you just have to add these guys, and that's it, right? And that's what Lange and Cernesi thought. They said, well, let's make a modified Donati conjecture. And this modified conjecture was that if the Clifford index, I will explain in a minute what that is, of C is at least 3, then P is injective. So basically, P is injective at all the double covers of C. I can say it like that, it's not very nice, but I'll fix it a little bit. Okay, so now what does this mean? The Clifford index is a nice invariant which people came up with because they were trying to look for something that was nicer than what people call the gonality. The gonality is the, if you have a, for instance, hyperelliptic curve, the gonality is 2. That means there's a map of degree 2 to P1. If you have a trigonal curve, there's a map of degree 3 to P1. The gonality is 3. So the gonality is the degree of the map, the lowest degree of a map to P1. A non-constant map. Well, that's, I guess, the constant map has like degree 0. Of a non-constant map from C to P1, right? So here we were concentrating on the gonality, but these guys said, well, the Clifford index is actually a much better invariant than the gonality. It tells you more about the curve. And these guys, it's true that these guys and these guys have got the same Clifford index. This is Clifford index 2. And so is this, right? So, so what is the Clifford index? The Clifford index, instead of just measuring the lowest degree of a map to P1, what you do, you take the degree of any map to any projective space, and you subtract 2 times the dimension of that projective space. So it's the minimum of D minus 2R, where there's a map where D is, let's say, less than or equal to the genus minus 1, and there's a map from C to PR of degree D. You see, so instead of just looking at P1, it makes more sense to look at all projective spaces and maps to those projective spaces of small degree. And then you have to adjust by this just to make it a little bit nicer. So now if you compute that here for the tetragonal, you get 4 minus 2, which is 2. For the plane sextic, you get 6 minus 4, which is again 2, right? So the trigonal curves and plane sextants index 2. Now they had some reasons for making that conjecture, just like before, just as I said. it had again something to do with the singularities of the theta divisor. Because it turned out that you can actually get the curve C by intersecting some quadrics in a projective space, and those quadrics came from the singularities of the theta divisor, and it turned out that if the Clifford index was at least 3, you could get the curve back from the quadrics. Now the only subtlety is that they got the curve back from the quadrics, but those were not just the quadrics coming from the theta divisor. They didn't know whether it was just those or whether there were some extra quadrics. If they did, they could have answered the question completely, right? They didn't have to conjecture. But they were hoping that maybe all the quadrics actually did come from the theta divisor, in which case, you know, the conjecture would be true. I don't know if that makes sense, but anyway. So all right. So in short, what I'm saying is that you can get some quadrics from the theta divisor of the prim and they contain the curve C in some projective space, but and in some cases you can get the curve C if you know the quadrics, but obviously, I mean, okay, so but you cannot always get it, and that's what I'm going to talk about today. It's a theorem due to Lange and myself, is that for any, so the conjecture of Lange-Sarnezi is false for any integer n, there exists C of Clifford index greater than or equal to n, such that the prim map is not injective at any double cover of C. So this basically kills any connection you could have hoped to have between the injectivity of the prim map and the Clifford index. So it's just more complicated than that. So I don't know what the answer is, where it's injective, but that's where it's not injective. Yeah. Anyway, so I will stop here. I'm out of time. I was hoping to say something about higher dimensions, but never mind.
Any questions?
Well, what are they?
Oh, these curves? Okay, you want to see the construction? Alright. The construction is very simple. It's actually quite surprising that people didn't see it before. So, you look at, so it's the tetragonal construction, but you change the base curve. So what you can take, let me see, so I will take a double cover under amplified. And what I'm going to do though, this curve is not going to be a generic, the general curve. I'm going to take this to be an associated cover. And of some curve, of a smooth curve y. And I'm going to take this guy to be simply ramified. Right? Now it turns out that you just have, this is, and then you can, well, for that construction you have to take n plus 4, right? And Alright, so if you have this kind of setup, that's degree n, then y embeds inside x to the symmetric power n. So then you can form a fiber diagram. So x to the symmetric power n, x tilde maps to x. Here you have y, and we define c tilde to be the pullback of y. So basically you can you think of y as being sitting in there by taking, you take a point little y in y, then you have n points in x, right? So let's say, I don't know, x1, xn, they all map to y, right? This guy, what does it do? It sends little y to x1 plus xn, right? And here, when I take the inverse image, I'm taking n points in x tilde that map to those n points in x. So that's what I'm doing here. And now you can, this curve xc tilde can have either two components or one component, okay? So, one or two connected components. And we're going to assume it has two. And that automatically happens. This automatically happens if y is P1. If y is not P1, you have to assume it, because it's not necessarily true. So, okay, and then, what happens is that, so you write, we haven't actually, I don't think we computed that. No, I may. But we did it in the case n equals 4, and it's isomorphic to this. And then how do you get the high Clifford index is by making the y big. So if you take, because y is not P1, you can take the genus of y large enough. Genus of y large enough implies that the Clifford index of x is large. Okay? So you have to do some computations.
In y generic somehow.
Y generic, yes, that's right. Y generic, very big, and lots of ramification points as well. Large ramification points. Genus of y has to be big, the ramification has to be big, and then it turns out that this guy will have very high Clifford index. And yeah. And that's it. So in the case of P1, you know, the construction is more or less the same, and that's the diagonal construction. There were several proofs of this isomorphism in the case of P1. None of those works in this case if y is not P1. They were all specific to y equals P1. So we had to come up with a new proof, which works also when y is P1. So it seems to work.
This cover is again unramified?
Which cover?
Ci tilde over Ci.
This one, yeah, those are unramified, yes.
So you get a, so it's a principally polarized print.
It's a principally polarized print, they're unramified, yeah. And they're not, the two curves, these three curves are not isomorphic to each other. You can do that by simple generation argument. You can make one of them singular and then the others will stay smooth.
They have different genera, don't they?
No, they have the same genus if n is 4.
X and the Ci have the same genus?
If n is 4.
Even if Y is positive genus?
Even if it's, yes, that's right. If n is different from 4, then these two have the same genus, but X has a different genus. Right. But if n is 4, all three have the same genus.
Other questions?
Can you tell us in just a few words what you were going to tell us about higher dimension, just a punchline?
Oh, okay. All right. Yeah, well, I was just going to, because I think the problem is very interesting also in higher dimension. I was just instance, the Bar's proof of generic Torelli for prims, let me maybe mention that as an example. It was motivated actually by a higher dimensional case, which is the case of intersections of three quadrics. So if you take an intersection of three quadrics, in P, I think, P2N, yeah. In P2N, for instance, then it has a, you know, this is an intersection of three quadrics, so you have a net of quadrics. It has a discriminant curve, which parameterizes the singular quadrics. There are three independent quadrics that contain T, and they generate a plane. And in that plane, you have the singular quadrics that contain T, and the discriminant curve parameterizes those. So the discriminant curve is a plane curve, and you can compute the degree. It has degree 2n plus 1. And so the intermediate Jacobian of this guy the intermediate Jacobian of T, which is defined in terms of a Hodge structure, so it's H, let me see, the dimension of this is 2n minus 3. So I have to take H 2n minus 3, 0. H. It's similar to the construction of the Jacobian. So I take some differential forms, and I take the dual, and I modify the homology. Jacobian is isomorphic to the prim variety C tilde to C, to a certain corresponding to double cover here. And so he proved Torelli for these intersections of three quadrics by using Torelli for prims. So he proved that actually the prim map is injective. So it's injective everywhere if C is a plane curve of degree at least 7. And from that he gets Torelli for this higher dimensional guy, because if he knows the intermediate Jacobian, then he knows the prim variety. If he knows the prim variety, he can get the double cover. And once he had the double cover, he can recover the T, because he can recover all the quadrics that contain T. Because basically the curve gives you the singular quadrics, and then from there you get the entire, you get three different quadrics that contain T, and then you cover your T from it. So this implies that the intermediate Jacobian of T determines T. Okay. And in general, I guess Torelli in higher dimensions has got to do with Hodge structures. For those people who are coming to my second talk, this will be helpful. You can ask, given any variety, any smooth projective variety, over C, you can take its cohomology, right? And you can get from that what we call a Hodge structure, right? And so then you can ask the Torelli question again. when does the Hodge structure determine the variety? So the first case is the Torelli theorem for curves, because the Jacobian basically is the Hodge structure of the curve. And this prim Torelli is another case of that, because we're taking the difference now between two Hodge structures of two varieties. And then you can go to higher dimensions. That's the case of an intersection of three quantities. You take the intermediate Jacobian is more or less the Hodge structure. It determines the guy. And I guess one of the most spectacular successes of this is for K3 surfaces, right? So if X is a K3 surface, then X is determined by its homology. And that means basically that if two K3 surfaces have got those isomorphic homologies, then the surfaces themselves are actually isomorphic, just like with the case of curves. If two curves have isomorphic Jacobians, the curves themselves are isomorphic. And so this is the nicest case in higher dimensions, but there are a lot of other results with, again, you can do generic Torelli, you can do infinitesimal Torelli, and things like that. So maybe I shouldn't spend too much time.
Thank you. Let's thank our speaker again.